Okay, let's get started. So today we have Christoph from McGill who will present their research on equality saturation meets machine learning. So it's going to be a very interesting talk with some interesting things about compilers and machine learning. So just few house rules. Like if you have a question during the middle of the talk, just raise your hand and I'll pass you the mic. And for people online, just type your question in the chat, and I will just at the right moment I will just convey the. I will either unmute you or I can like convey the question to the speaker. And also at the end of the talk, we have like 10 to 15 minutes for questions. So yeah, that's all. And with that, let's get started.
Okay, great. Thank you very much for the introduction. So good morning, everyone. It's my pleasure to be here. So I'm actually at McGill, but I'm also an associate member at MLIR, although I rarely come here. And the goal today for me is to present some of the research we're doing in my group related to compilers and in the hope of establishing collaboration with the expert in machine learning, because we are more user of ML rather than designer of new fancy techniques, but we design new compiler techniques and we want to use ML to make that great. So the talk will be in 3 parts. They're not divided equally, so I have already to admit that the ML part is going to be relatively small, 20% perhaps of the talk, because this is really the work we want to do with the technique that I will explain to you at the beginning. So we'll start with talking about compiler optimization and what is equality saturation. We're then going to follow 2 use cases. We'll see how much time we have for this that my group has worked on code idiom recognition and integrating MLIR with equality saturation. MLIR is one of the big framework out there to do compiler optimization. And finally, I will be talking about the opportunity to apply machine learning to this and some preliminary results that we already have from my students, actually Adam Musa, who is here, and is my Mr. Machine Learning in my group, who is basically applying these techniques to compilers. All right, so first, what is the state of compiler optimization? So the big framework that everybody in industry is using out there, although you may not be aware of it, is MLIR. And MLIR stands for multi-level intermediate representation. And if you're not familiar with that, you may have heard perhaps of LLVM, which is the de facto production quality C compiler that everybody uses in industry. And MLIR can be thought as a superset of LLVM. Whatever LLVM can do, MLIR is also supposed to be able to do it. And the main idea of MLIR is to basically break down the representation of programs across different domains of abstractions. And we will see later how that makes optimization easier to implement. So MLIR has what they call dialects, which is the ability to define operations at different levels of abstraction. Perhaps you want to think about scalar arithmetic, modulo, multiplication, division. Perhaps you want to think about linear algebra, and that's the big thing, obviously, for machine learning. You have operator like matrix multiplication or matrix vector multiplication, dot product, and so on. Perhaps you want to think about your program in terms of loops, in which case you can express them with control flow, like for loops, or maybe if then else. And of course, you could also think of your program in terms of plain LLVM IR. And in MLIR, there is basically a dialect called the LLVM dialect that can reproduce everything LLVM can do. Now, the reason why we want to do that, because it makes it easier to go from high-level abstraction down to optimal code. So I took an example here of how would you go from something described in terms of linear algebra operation to CPU assembly. And the way you do it with MLIR, you go through this different layer of abstraction. You start with linear algebra operator. You turn then that into for loops. You then turn that into LLVM IR. And then finally, you can get your assembly out. And what it also allows you to do is encode domain-specific optimization at a much higher level of abstraction than typical compilers do. Typical compilers, like LLVM, will reason in terms of for loops. If you write matrix multiplication, the LLVM compiler will only see for loops, and it's going to try to optimize your matrix optimization by maybe swapping 2 loops, tiling the loops, and doing lots of complex optimization. But if you remain at the domain of abstraction of linear algebra, you can, for instance, very easily tell the compiler perhaps about associativity of matrix multiplication and tell it, hey, if you do A times B times C, it's equivalent to A times B times C. And we will see later examples of why this is a good thing to tell the compiler about. So MLIR, again, in case you're not aware, it's being gradually integrated into all ML framework out there. TensorFlow, PyTorch, pick your favorite framework, it is in there. This picture here is actually from Google, it's not mine. And this is giving you basically the way you then turn the TensorFlow PyTorch program into code that can run on GPU, CPU, FPGA, the tensor processor unit from Google, or any other accelerators there. And you're going through basically different dialect, different domain that you have in MLIR. First, you're importing your graph, which will have operators on the graph, operations on the graph. Then you perform some optimization, some conversion. You lower the graph little by little to something that looks more like the operation that will finally execute on the hardware. At the end, you generate code, but in the process of generating code, you perhaps fuse operators, choose different kernels that have been highly optimized for the target architecture, and so on and so forth. And all this is now happening in MLIR. Or if it's not yet happening in MLIR, it will be done all in MLIR in the next couple of years. So how do people express optimization? So already I mentioned that earlier. People think of optimization and they group them by domain. So perhaps you want to tell the compiler about arithmetic optimization you can perform, such as a divided by 2 is equivalent to a shifted to the right by 1, if you think of integer computation. So this is quite low level, but it is really well known. I'm assuming even machine learning people knows about this type of trick you can play. A divided by a is 1. Of course, there's an asterisk here if a is different than 0. I'm just omitting some details. You might talk about associativity when you combine multiplication, addition, and perhaps some simple rule like a times 1 is equal to 1. But then you can also do the same in the domain of linear algebra and explain properties that your operators have, such as associativity of matrix multiply, or the fact that if you multiply a matrix by a scalar, this is commutative. You can multiply first scalar times matrix or matrix times scalar. And we will see how this is useful to actually produce code that runs fast. So now, how do compilers typically optimize? So the typical way right now, today, that they do that, they have a set of rewrite rules. Basically, you kind of properties of your operators. You have a cost model telling you how expensive each operator is. Division is usually typically much more expensive than multiplication, which is itself more expensive than shifting the bits to the right or to the left. And you have an expression that you want to optimize. I'm taking here, of course, a baby toy example just to illustrate the concept in this talk. Let's say your program is just 2 times x divided by 2. Of course, a human would notice that, well, this is just x. But how does the compiler get to discover, hey, this is just x? So what he will do, current state of the art, is greedy fixed point iteration. The idea is that you go through all the rules that you have, you apply them one by one, as long as the costs get lower. And then once you are done and your program cannot be further optimized, you stop and you say, job is done. So let's have a look at what happens if we take this rule in the order 1, 2, 3, 4, and we apply it to this expression. So the first rule that we apply is number 1, the division inside the x divided by 2 gets turned into x shifted to the right by 1. Now we look at that and we ask, can rule 2 applies? No, there's nothing that divides itself. Can rule 3 applies? No. Can rule 4 applies? No. We go back to rule 1, can it apply? No, there is no more division, we're done. And that has a cost of 3, which is obviously not the ideal optimal solution that we want. So how could we fix that? Well, perhaps we can change the order in which we apply the rules. So let's try with a different order, 3, 2, 1, 4. So if we do this, we first apply this rule number 3. Again, these rules are a bit arbitrary. I picked them to make the example work. You would realize that you get the x outside, and you have x times 2 divided by 2. Now the rule number 2 can apply. You get x times 1. Now rule number 4 can apply. 3 does not apply anymore. 4 applies. You get x. And that has the optimal cost of 0 because there is no operation left. Okay. So now you may say, okay, so we can solve this type of problems by simply reordering the rewrite. And this, by the way, what is happening here is we fell into a local optimal trap because we too early applied the rule to shift things to the right by 1 rather than division, which was actually a bad idea in this example. But for any given order of a rule, I can come up with another example where that will not work. Here's another one, x times 2 divided by 2. If you apply the rule in the same order as the last one we did, then you would end up with 2 times x shifted to the right by 1, with again a cost of 3. So what this shows you here is there is no way to have a fixed ordering of the rule that leads to the optimal solution with this set of rules that I have here. Okay. And this is known in the compiler jargon as the phase ordering problem, because this applies to things that are much more complex than just a times 1 is equal to a. Imagine what the compiler does. It's inlining functions. It's unrolling for loops. It's doing things called constant propagation, common subexpression elimination. If you have a little bit of compiler background, you know perhaps what I'm talking about. You can get an idea. And basically, this is much more complicated than the little example I have here. So this problem, basically, phase ordering problem. And the solution to that is basically equality saturation. So this is a technique that came out in 2009. Apologies, you can't see the bottom right of the screen here. And it is slowly making its way into compilers, but we will see that there is a big problem with that approach. So the idea is we want to store, when we are applying rules, all intermediate program variants that we could think of as we are applying rules. And we build a data structure called an equivalence graph, or eGraph for short. The eGraph has two main components. It has e-nodes, equivalence nodes, which represent your operations or your leaves, like a constant, a variable. And it has e-classes, which is a set of e-nodes that are all equivalent to one another. And we apply a process called saturation, where the idea is that you're applying rewrite on this data structure called eGraph until you can no longer modify the data structure. And at that point, we say that we reach a fixed point and we can stop and then have an extraction phase that basically extract the global optimum from that graph. And the important aspect here is that the rule order does not matter for this process. So let's have a look at how this works in practice. So let's go back to our example, 2 times x divided by 2. In a classical compiler, this is represented as what is called an expression tree. This is actually not a tree, I'm lying here. It's a direct acyclic graph. It's a DAG. Just because in compilers, we love to try to be optimal. So we're not going to instantiate 2 nodes 2. We're only going to have 1 because 2 is always 2. Okay. So everybody can see how this is equivalent to 2 times x divided by 2. I don't think I have to explain the visual picture, right? Okay. So now this is what the classical compiler does. What equivalence saturation does, it adds little boxes around the nodes, and now we're saying that these are equivalence classes. So in this box, will contain all the trees, subtrees, or subdag that are equivalent to that node. And the other difference, as you can see, is instead of now pointing to operation, we point to equivalence class of operation. So you will see, as I will build up the example, that this equivalence class will be populated by other things than the one we're seeing here. So let's have a look. We have our set of rewrites, and now we're going to do the process of saturation of the graph. That means we're going to apply the rewrite and see how this eGraph gets transformed step by step. So first, we look at this rule, a divided by 2. So we notice there is, of course, some logic to detect the patterns in the graph, that there is division of a, which in this case is x. A could be anything, right? And on the right-hand side, you have the value 2. So we have identified this. It means that we know that this division here is equivalent to shifting a, whatever a is, by 1 to the right, okay? So that means we're going to be adding a new operator in the equivalence class of the division to say that whether I divide x by 2 or whether I shift x by 1, you also observe a new node appear with a new equivalence class, which is anything that should be equivalent to 1. These two things are equivalent. Does it make sense? Yeah, okay. And then we continue this process. We then look for, do we have a divided by a? So the division is only in the equivalence class on the left. We see that's actually x divided by 2. It's not the pattern, so a divided by a. Therefore, this does not apply. Then we ask, oh, do we have a times b divided by c? Yes, this is, if you follow the arrow, this is the highlighted nodes in green, in which case we can rewrite that into b times a divided by c. And we will see that a new node will appear in the equivalence class of the multiplication up there. And we continue this process. We're going through all the rules, and little by little, and observe that sometimes the equivalence class gets merged. For instance, at this point here, I see that I have the equivalence class of 1 here, an equivalence class of something that is 2 divided by 2. And at some point, I apply the rule anything divided by anything is equal to 1. And at that point, this E-class will merge. So we can discover that two things that at first look different suddenly are equivalent. And the idea is that by the end of this process, you have built all possible variant of the program encoded with these equivalence classes. Now, of course, someone might say, hey, what about the number 2 there? Why is it not equivalent to, 2 divided by 2? What about 2? Why is it not equivalent to 4 divided by 4, for instance? Well, just because in the set of rules that I have here, I'm not talking about the value 4. But if you had such a rule, perhaps the graph would get more complex. Okay, so now that we have this graph, this is a data structure that basically it's a finite data structure that can capture all possible program variants based on these rewrite rules. And now we can extract the best variant. And we apply a cost model. So we have the cost of the operator over there on the top left. And we're going to do an approach. This is called in compiler jargon. We do a depth first search, post-traversal order, of this graph, and we assign the cost first to everything that is at the bottom. Think of it, we go recursively, then we come back up, and at each point, we remember what was the best of my options. This is also mixing dynamic programming in there, for those of you who have, I think all computer scientists know dynamic programming, I would hope. Okay, so you do this, you can attach the cost to each node. Then once you know the cost of each node, you can find the minimal cost for the E-class, and then you know what your final solution should be. And because our original application was 2 times x divided by 2 up there, this is the E-class we're interested in, and we can find that in class, the operator x, sorry, the variable x that has cost 0, obviously, it's just the value, and that becomes our optimal. Okay? So this is equality saturation, very simple. The beauty of that, you can apply that to many different domains, not just software, you could also do it for hardware. People do that with AND gates, OR gates, for instance, if you design an accelerator, etc. So this is really a generic optimization technique, not just limited to compiler software. So now we're going to see some use cases, what we have used that for in my group. And the first one is called idiom recognition. This is the work of my PhD student, Jonathan. So what are we trying to do here? Well, as you know, we have lots of different types of hardware that exists out there. CPU, GPUs, FPGAs, tensor processor units. It's a bit hidden there, but machine learning accelerators, basically. And if you want to program these, typically people will use some form of high-performance library framework. I call them a library in this talk, but PyTorch, TensorFlow, BLAS. And you're having basically an interface that you're using to target these devices. And the typical interface is, well, you have operations like matrix multiply or matrix vector multiply, dot product, tangent hyperbolic, etc. And you as a programmer, using this operator, you combine them, compose them to get your application. But the question now is, what if someone writes an application without using this interface? Okay, or perhaps they use one interface, they use a BLAS interface, but you're trying to target TensorFlow or PyTorch, because perhaps PyTorch and TensorFlow can target your TPU, but not BLAS, or vice versa. So how do you go from something that does not use this library interface to a program that actually makes use of it automatically? And this is what we're going to see how we do that with equality saturation. So first, it is important to think of a domain of abstraction. So you can have domain-specific languages, like dot. This is a function to do the dot product. You may have that as a programmer and you directly use dot, or you can do low-level system programming for loops, variables, arrays, pointers, etc. And in between, you find functional programming or array programming, if you like. And the idea is that you represent your program in a more algorithmic way using a primitive such as reduce, map, or zip. So I'm giving you here a little illustration of how a dot product would be expressed with these building blocks. So dot product, you get 2 vectors in, you first zip them together, so you're getting pairwise elements. You then multiply these elements pairwise, that's the product, and then you reduce, you do a sum to get your final value out, and that's how you're expressing a dot product. And this functional programming is basically a very good intermediate level between high level like dot product and low level like for loops and array, because it gives you a little bit of implementation details. It describes the step you need to do in order to perform a dot product without going into the details of what memory do you access. Do you need a pointer here? Do you have a for loop? Do you have an iteration variable, etc., etc.? So you have some flexibility, and it's relatively simpler than C. So what we're doing in this work is we're taking the library interfaces, like for instance, BLAS or PyTorch has a function dot, and we express them in terms of this functional primitive, as we've seen. And now when someone comes with an application, if they express the application with the same functional primitives, these are basically the nails, the hammer is dot. We have a library that can perform dot product, but perhaps your program is dot product, so you can easily use the dot function from your library. What if you're trying to do vector norm, and the only thing you have, the only hammer you have is dot product, because that's what your hardware does. It only does dot product. Well, in functional, it will be reduce, map, and I won't go into too much details here, but this is basically explaining to you what the vector norms is. You just multiply pairwise all the values, and you will struggle here because it does not match the definition of your dot functional unit, which is obvious because this is the vector norm is not the dot product. What if you're just trying to sum an array? Very silly. This is just reduction, a reduction with a plus operator. But again, that does not match what you have up there, because dot product is reduce, map, zip. This is what we call an idiom, by the way. And this is what we're trying to do. We're trying to recognize in that program array sum or vector norm if we can find a dot product in it. And if you're a human, you would know how to turn a vector norm or an array sum program into a dot product. Any guess? How do I make use of a dot product operation to implement vector norm as defined here, or array sum? Yeah, I just repeat x's twice. How do I do an array sum? Well, I do a dot product with vectors of 1. Okay? So the idea now is that we're going to try to find a transformation that basically gets us from a reduction with just plus to something that basically do dot product with a vector of 1. And if you can do that, it means you're able to exploit this dot product hardware, because you imagine someone has spent a lot of time optimizing the dot product function in your hardware to perhaps sum an array. Even though that sounds silly at first to add the vectors of 1, it might actually be faster than doing it sequentially on your CPU if you have the parallel hardware. So there are 3 ingredients that we're going to be using to achieve this goal. The first one is the IR, the intermediate representation. We're going to be using here a functional IR. So we're going to try to reduce the number, think of it this way, we're going to try to reduce the number of operators that we have in our language, that we're trying to recognize these idioms, to the minimum. And here we can, everything boils down to build and iFold. And I will explain this in a second. Then we're going to have some rules that will explain basically that will define, on the one hand, your API interface. For instance, BLAST and PyTorch has a function to fill an array with a constant. How is that equivalent with our IR? We can give it a definition. And it will also explain property of the IR. So build here builds a vector of size n, where the elements, to produce the element, you call a function f at each position I. And this rule is simply saying that if you're trying to index this vector, it's equivalent to calling the function with the index I. It's just kind of defining the primitive. And then we're going to be using equality saturation on this type of program representation to basically try to find the idioms in the code. So first, the minimalist IR, we have just 2 primitives, build and iFold. Here is the kind of visual semantic idea of what they do. If you say build 3, f is a function, it means that you're building an array of 3 values where the element is f called with 0, f called with 1, f called with 2. With this primitive, I can create an array of constant. I can create an array that has 1, 2, 3, 4, 5, 6. Or I can create an array that looks up values into another array, for instance. And the other one is iFold. And fold is simply you taking a function f, you're taking an initial value, and you also have an index that comes in, and you apply f to the initial value, your accumulator, and 0. And then you apply again f on that new value you've produced, and 1. And then the new value you produce, and 2, etc. And with these 2 primitives, you can express all the other functional primitives that you typically use if you're a functional programmer, like zip, map, reduce, concatenations, etc. So the idea is that you go down to a very, very minimalist IR that only contains a couple of operations, because that makes it easier for the compiler then to reason about this operation, and it makes it easier to write optimization for them, because you only have to be bothered with this operator, and then everything else will fall into place. So if we go back to our example, this time with the minimalist IR, what we're going to be doing is rewriting this reduce map zip in terms of this iFold and build. And now this is what the compiler will see. Dot is equal to an iFold with something a bit complicated inside. I won't go to the detail, but this is basically the definition of dot in terms of iFold. And now you have the definition of the dot product in terms of iFold, which is the same because that's the definition of dot. And we have the vector norm, and we have the array sum. As before, we see that the dot product, of course, it's equivalent to dot by definition. But the vector norm now, we can see it's much easier to notice that, hey, I need to use XS twice because this XS at I maps this one, and that XS at I maps this one here. So it becomes now trivial for the compiler to realize, oh, this is dot XS XS. The last one still remains a little bit cumbersome because here we're expecting a multiplication, but here we don't have a multiplication. That's where equality saturation comes in. Why? Again, we'll give you the intuition, because we know that multiplying by 1, A and multiplied by 1 is equal to A. So the idea is that there will be a program variant here that is equivalent to this array sum, where I'm performing a multiplication inside. And if I can find that, few equality saturation, then bingo, because I will have the pattern I'm looking for, something multiplied by something else. It's a bit tricky because it's not just the one I want to index an array. So I'm going to have to build an array of 1, and then I can index it. Okay. So then we're having our language rule. I mentioned that before. We're having the idioms encoding into the same language. We have equality saturation, the same picture as before, except the colors are a bit different. And now we can combine them all. So we can start with an expression. This is the array sum, that not mistaken, again. The last one we were trying to find, and that's its representation. Again, I won't go too much into the detail, but now we're going to be applying the rules one by one, and this E graph will grow. And at some point, you notice a field appeared here that's to create an array of 1. And now I find my dot magically with equality saturation. Okay, it just happened naturally. And now I can see that indeed this array sum program is equivalent to a call to dot. This first argument XS and the second argument fill me an array with 1s. I'm omitting here the size of the array, just to keep the example simple. All right, so end-to-end example. This is what we do in terms of evaluation. We take a program written in C. We take a benchmark suite called Polybench, which has been used in the context of polyhedral compilers, for those of you who knows about compilers. We take this, we manually transform that into our IR. This step, I've noticed, could be automated. In this example, we did it manually. So this complicated C programs turn out to be a couple of build nested with some code. We then apply equality saturation, and we notice that this program, this complicated C program on the left, is equal, if you're targeting PyTorch, to a build of a core of matrix multiplication with matrix being transposed. Then we give that to a Python code generator, and we get a Python code that would call PyTorch from this C program. Okay. Now we can do the same, but targeting perhaps a different library, BLAS, which is a much older version of all this type of framework. But in BLAS, the interesting thing is that there is a gem. Gem is generalized matrix multiply. It's not just multiplying two matrices. Gem is alpha times A times B plus beta times C, where A, B, C are matrices, alpha, beta are scalars. Okay, so we can also target something that looks a bit more complex than just matrix multiply. And super important, it's super interesting, we also exploit the fact that this library can take Boolean value here to tell you whether the implementation should transpose or not your matrix. And we can automatically figure out, hey, this argument should be true, because that's going to correspond to implicitly doing a transposition of it. So that we do not need to actually make a call to the transpose function here, which may be time-consuming. And this has to do with the fact that the BLAS library has several implementations of matrix multiplication for all kind of cases. Both transpose, non-transpose, one transpose, the other transpose. So they have to start 4 implementation behind the scene. Okay. And similarly, we can do C code generation, because BLAS is a C library, at least the one we've used, or we could think of cuBLAS if you are getting NVIDIA GPUs, and we will get our little piece of C code. I'm not explaining how we do the code generation. We have a whole paper on that, but that's probably not what people are interested in. The important thing is we can do that. We can do this translation. So the idea here is, again, we can start with something like looks like C. We do a human translation. This step could be automated, and then you get BAM directly to code that can exploit a library that has operators that are implemented with high performance implementation, or perhaps can be accelerated on a hardware device. So does it work? Well, we had a small collection of benchmarks, the old benchmarks that consist of several for loops nested into one another. And this do-it-gen benchmark I was looking at, we see that compared to taking a C compiler, generating code for the CPU, versus using the BLAS CPU C library, we can get a 2x speed up by just doing this. For the other benchmark, the speed up varies, but we can get large speed up. This one is not surprising. This is 1 mm, it's matrix multiply. Someone wrote matrix multiply in C, give it to LLVM, we give it to LLVM, run on the CPU, and then what we do, we take this C code, we turn it into this functional language, we then use equality saturation, find out that, oh, it's MM, it's directly a call to gem, right? And then we get a 20x speed up automatically. Okay, so that's quite good. For some of the benchmark, we get slowed down. It doesn't always work out. And the reason is sometimes it might be better to generate the for loops in C because perhaps the library does not have a pattern or the API interface, we have something that is maybe slower to use. I go back to the example of summing an array. You remember summing an array, we need to first create a vector of 1, then we call dot product. Perhaps for that library, that's slower than directly emitting the for code, the C code with the for loop that just sum my array without creating the array of 1. Okay. It depends on the benchmark. Okay, now the problem, because there is a problem, is that saturation, equality saturation is extremely slow. So if we look here at this graph, we took this benchmark that we had before, and we look when we're targeting PyTorch, the number of steps in the saturation process. So what is a step? A step is we take all the rules, we apply them once, and that's one step. And then we repeat. We apply all the rules again, we apply them once. And we're going to see here how many e-nodes we have in the e-graph. So the size of the e-graph as a function of the number of saturation steps. And as you can imagine, this grows exponentially. Okay? And we actually have to stop after a while, because I think here this is after 3 hours compute time of saturating. And this shows you here what solution we found. So remember, this was the example where we had a matrix multiply with a transpose. So if you just do 1 iteration, you only find a dot product. You won't find matrix multiply. 2 iteration, not it better. 3 iteration, you find a matrix vector multiplication in there. And finally, after 4 iteration, you find the solution that you're looking for. If we target BLAS, similar story. Of course, the curve looks similar. The patterns we're looking for are different because it's a different library, but same issue. So I will take the question in 1 sec. So basically, the bottom line is you have this exponential growth in the size of the graph and in the time it takes to saturate, which is bad news. Yes?
Is this counting like the size of the equivalence classes, or is it like the number?
This is a number of e-nodes, of nodes in the e-graph.
Right, but like okay, so but a node in the e-graph could be like an equivalence class of operation. Right?
So there are 2 types of nodes. We have an equivalence class node. So equivalence class is a group of nodes, of e-nodes. Yeah.
Okay, so like if you have like a huge equivalence class that's going to show up as like
correct. Yeah, yeah. We have other data that shows a number of equivalence classes and not the average number of nodes in the equivalence class, but they would show similar trends. That things grow. Yeah. And you should remember the example at the very beginning of the talk. We start with something as simple as x, whatever, 2 times x divided by 2, and it becomes already 10 or 20 nodes. So imagine this is a bunch of nested for loops with a lot of computation happening in there. Yeah. Okay, so this is bad news. Next one, how am I doing with time? How much more time do I have? 15. Okay, so I'll speed through this use case to reach the machine learning part of the talk. Let me try to do that. So here, what we're trying to do, it's another small use case where we now try to integrate equality saturation with MLIR. MLIR is this compiler infrastructure I talked to you about. We're trying to see how feasible it is to add this technique to MLIR. This is the work of Aziz, one of my MSc students in my group. So we're focusing here, for the purpose of this talk, on the matrix multiply example. So as you all know, if you have multiple matrices to multiply, in this case, this is called 2mm. We do 2 matrix multiplications. We have 3 matrices, A times B times C. The number of operations that you have to do depends on the order in which you're multiplying your matrices. Okay, again, for machine learning people, this should come at no surprises. If you look at this small example, if I first do A times B, then times C, that will lead to about 2,000 multiplications. On the other hand, if I do A times B times C, I'm down to 1,000 multiplication. And it has to do with the fact that these matrices have really odd shapes. If they were all square, the order does not matter. But as soon as they're not square, you will end up with a different number of multiplication. That makes sense to everyone, right? Okay. Now, of course, things get worse if you have more matrices to multiply, like 3mm, for instance, which is 3 matrix multiply. And in this case, you see that there are a lot of different permutations. And now, what we're going to do in this use case is see how, first, this benchmark is expressed in MLIR, how we can rewrite to express all these different ways we can change or we can reassociate the operation and the type of performance that we get. So in MLIR, the purpose of the talk is not to teach you MLIR, but it's just to give you an idea. This is what we're dealing with. This is the representation of A times B times C times D in MLIR. There is a lot of of information here that has to do with the type information. MLIR store the size of your tensor, and you can guess tensor bracket 2010 I64 tells you it's an integer 64-bit integer of a matrix that is 20 by 10, and that's our matrix name. And then you have the operation here, and this is how they appear in MLIR. So a matrix multiply appears just as an operator. And this is really similar to assembly programming, right? It's really one operation at a time. So now what we did is we developed a framework called dialeg, where we take MLIR representation of a program in, and we spit out an optimal MLIR program. Inside, we actually make use of an accurate saturation engine. It's called egglog. I will show you in a sec how that looks like. We have a set of rewrites. We have a cost model. And the rewrite that we're interested in here is associativity of matrix multiply. And the cost model basically is multiplying the number of rows of X times the number of columns of X times the number of columns of Y. That is the cost of the computation, okay? If you want to perform X times Y, where X and Y are two matrices. And what we have developed here is some tools that translate MLIR to this representation called egglog. It's an accurate saturation engine that you can actually try at home if you're interested. It's very nice. They have a demo online. You can write some rules, write an expression, press play, and you see step by step the graph being built if you're interested. And this is how in egglog we specify our rewrite. So far I've shown you rewrite rules for human consumption. This is rewrite rules for compiler consumption, okay? So this is the rewrite rule, X times Y times Z is equivalent to X times Y times Z. So it looks scary at first, but it looks scary because in the compiler, we have all extra information we're carrying around. For instance, the type information, the shape of the tensor. But you can see clearly here that this line over there, this is basically a math mode of a math mode of XY times Z. This underscore T, it's about the type of the tensor. Because when we do this operation and we will start to rewrite them and rearrange them, we need to also keep track of the type information and rebuild the proper tensor shape after the operation has finished. So for instance, once you do X times Y, that shape over here where my finger is obviously a different shape than the one that is down there or the one that is in the middle here. So this rule also includes the fact that we have to recompute this shape. And this is what is highlighted here happens to be about the type. But the bottom line is there's a little bit of syntax. There is some weird stuff called union. But the idea is by writing this, you're telling the compiler these two things are equivalent. So if we do that, we can take the original program on the left. It goes for a whole machinery. And on the right, you spit out the new optimized program. Obviously, it doesn't look much different because all we're doing here is we're reordering the order of the operation on the matrices. And on the case on the left, that would cost 10,000 operations. On the right, only 5,000. So the really cool thing I think here is that this type of optimization, they are actually changing the algorithmic complexity of your program, right? Which I think is quite cool because usually compilers don't do that. You're relying on the programmer to tell the compiler, you know, this is the order in which I want the operation to be computed, and you hope that you don't want the compiler to start to change that because perhaps you as a programmer knows that certain matrices have certain shape and it's better to do it in this order. But here we can actually let the compiler change that if it has the information about the size. Okay, again, what is the bad news? Well, saturation time is again exponential. So here, just focus on the highlighted columns. I'm showing you here the benchmark. This is 3 matrix multiply. This is 10 matrix multiply. So we have basically 11 matrices we're multiplying together. This is 18 matrices. We're doing here a study of how things scale. You can see that saturation time increased dramatically. If we double the size of the number of operations that we have, the number of matrices we're multiplying, you're doing almost times 10 in terms of the execution time. So 18 matrix multiply, it takes 3 seconds for saturating. That might not sound too bad, but for a compiler, 3 seconds is an eternity. Especially this is just, imagine, matrix multiply. Your program is much bigger than that, typically, okay? So we again have this problem of exponential growth. And that brings me to the last part of my talk, which is how can we use machine learning to solve that problem of exponential growth? And this is the work of Adam Musa. So he started doing that since the summer. He's a master's student in my group. And what we're trying to do is use reinforcement learning to basically make accurate saturation work and not have to wait this crazy exponential time. So this is the big picture. We want to take the E-graph data structure that we've seen throughout this talk. We get an agent, and we want the agent to tell us what rewrite should I apply now on the E-graph, with the goal of not anymore saturating the E-graph, because if you saturate, it means you have all the possible program variant. But the goal is to find a good unsaturated E-graph and to stop before you finish saturating. And the sooner you can stop, the better. Okay? So the reward for the agent is basically the cost of your E-graph before you are applying a rewrite. What is that? The cost of an E-graph, we define it as you take that E-graph, extract the best expression you can, and let's calculate how fast that expression goes. And then we apply a rewrite, and now we get a new E-graph. And that new E-graph basically should have an expression in there that we can extract that should be faster than before if we pick the right rule to apply. Does it make sense? Yep. And of course, we subtract a small penalty because the goal is not to saturate. So we penalize the application of a rewrite. The name of the game is finding an E-graph that is really good is in as fewer possible steps that you can. So what kind of problem we're encountering? Well, first we need to encode the E-graph. So it's a graph, so we can use an adjacency matrix encoding. We have two types of nodes, another type of complexity that we have to deal with. We have nodes that represent the E nodes, the operation or the leaves, and we have the E classes. So in this case here, you could see, for instance, that the E class 1, everything equivalent to that division, contains just the division operator. The E class 2 contains multiply and shift. E class 2 contains multiply and shift. And if you look at the E node, let's have a look at this guy here. This multiply, which is over there, points to E class E4 and E3. The multiply points to E4 and E3. They are non-zeros here. That makes sense? So this is one encoding of the graph that we've tried. And then we use a neural network in the RL agent to basically predict which rule I should apply. And this is the current state of the research progress. I will admit, if you have any question about why we're doing things this way, ask Adam. He's coming up with this design. He started with something simple, and we grow it and realize, oh, it's not learning. What do we need to do? So we use some graph neural network layers, something called jumping knowledge that he was teaching me about a week ago. So you guys probably know that much better than me and Adam. And then we finish with some MLP layers at the end. In terms of encoding, we have a lot of problems to solve. For instance, this encoding here is an encoding that does not care about position, because usually when you have graphs, the order of the children does not really matter, but for a compiler it matters. If I do x plus x minus 1 or 1 minus x, it's very different, right? So this is the positionless encoding, where we just have 1 or zeros to encode the graph, but we also have another one that we call the incremental encoding, where we have the order. So for instance, this shift here is E4 followed by E5. The shift here is E4 1, E5 2. Of course, for a neural network, that's probably not very good because these numbers 1, 2, they're not like weights. It's not like one is twice as important as the other. It's just an ordering, right? So there might be a better way to do encoding. Another one we've tried is to think of a very different way to think of a representing program that's inspired from functional programming, where we see the world as functions, and functions are unary in functional programming. Anyone has heard of lambda calculus before? No? Okay, so. Yeah, okay, 1%. Yeah, the idea is all functions can only take one argument. If you need more than one argument, you create a function that gives you back a function that you can then call again. So you can chain functions. That's why it's called functional programming. You have functions everywhere. So with this type of encoding, we solve a bit the problem of not having to encode the position, because all functions only takes one argument. And here is how it works. Some preliminary result. I'll be done in probably 3-4 minutes. That's good, yeah. So what we did here, we decided to take an approach where we go from the ground up. There have been other people that have looked at this problem of using reinforcement learning for equal saturation, but they take the bazooka approach, I call it this way. They take a whole problem with like 100 compiler optimization, 100 rewrite, big application, and they just try their luck with a big machine learning network, and unsurprisingly, it doesn't work very well. Here, what we're trying to do is understand what we need to have. How do we encode the graph? What kind of architecture we need in neural net to basically solve tiny problem to start. So this first tiny toy example is a language. These are basically what you're dealing with that only has the constant 1 and 2 and the power operator. Don't get simpler than that. All you can express is 1 to the power 1 to the power 1 to the power 2. The name of the game is to bring this down to the smallest possible expression. The rewrite It's simple. 1 to the power 2 is equal to 1. 2 to the power 1 is equal to 2. That's all we have. So the RL agent just needs to pick which one of these two to apply. It's all it needs to pick. And actually, this was already hard to start. And here's an example. Perhaps you've been given this program as an input. And if you apply one of the rules, you can get this to be equivalent to 1. But you have to apply the rule, which one is it? You have to apply rule 1 twice in a row. So you rule 1 again, and then you get to 1. And this is the type of performance that we are getting. So there's a lot of lines here. Let me just show you what all this is. So first of all, this you're seeing here a measure of the average rewards that we're getting. Main idea, if you're hitting 1, you get the perfect path in the search. You found exactly the sequence of rewrites that is the smallest possible to lead you to the best solution. Okay? And in this case, because the program are very small, we generate 100,000 of this test program manually, so we automatically, and we know for each of them what the optimal solution is. So we know the go truth here. And what you see in yellow here to start, that's equality saturation. That's if you take all the rules, you apply them once, all of them once, then you apply again until the graph is not saturated, until the graph is saturated, and that gives you an average reward of around just below 0.6. And now what you're seeing here is random in black. We always love to do random. Surprisingly, for this tiny example, random is better than going to saturation. So hey, you don't have to learn much. But actually, we see that we can learn. The 3 other curves, red, blue, and green, this is just using different type of encoding of the graph. Unsurprisingly, okay, so this is, apologies, what I was highlighting with my hand. Reinforcement learning can learn, so this is great. Random is better than exact, and this is all good. But as you can notice, the positionless approach is less good than having the position encoding in the adjacency matrix. And that makes sense, because you need to understand if you have 1, 2, or 2, 1. You don't know if you have one or the other, how can you determine which rule to apply? Okay? So this was just a kind of, and you can see that this is similar to random, basically, right? Because if you don't tell me, is it 1 to the power 2, is it 2 to the power 1, if you cannot differentiate between these two cases, there's no way you can learn which rule to apply. That makes sense, yeah? So this is, again, what I mean by we're starting from the ground up, because we're trying to figure out what we need to do with the representation, with the reinforcement learning approach to get to solve this type of many problems. Then we move on to a slightly more complex problem with 3 rules now. So this is a different language. We have the number 1, number 2, plus n variables. And we say, I'm using an infix notation. Are you all familiar with infix notation? So this is really, I'm doing plus 1 minus 1. So I'm doing 1 plus minus 1. Okay? 0. The other rule tells me if I sum 0 and x, I get x. And this is associativity of addition. Okay? So if you just have these rules and you have a little example of how they could be applied, which one to apply, let's see what the reinforcement learning techniques perform. And we see that this is terrible, right? And that's with the architecture I've shown you earlier. So even for a problem as simple as that, with only 3 rules and 4 types of operation, of type of node, we struggle. But the good news is, I think I have this highlighted, if I click next, yes, is that we can learn something. So first, for that case, random is terrible, because now there are 3 choices, much harder to, by accident, get the right sequence. Exact is much more worse than before, again, because there are 3 choices, harder problem. But with the incremental representation here, we see that actually reinforcement learning gives us something that is better than equality saturation. Not yet what we want. We'd like to be here, but this is going in the right direction. Okay. We believe that there are little issues here, because now if you look at this type of rules, think of these rules, they're going to be trees or graphs, right? And you have multiple levels. If I have this rule plus, imagine there's a plus node, has 2 children, and then there's again a plus node, 2 children. You start to go deep in the graph, right? So I think when I was talking to Adam, my student, he told me, perhaps when we have more complex rules that are deeper, we perhaps need to add more layers in our graph neural networks to be able to go through these different rules, right? So perhaps we want to figure out, what's the relationship between the depth of a rule and the depth of the neural network that we should use. And this is, again, where I'm hoping that people in the audience could help us. We also, of course, have the case of this apply encoding. This is this kind of functional encoding. And here things get really, really bad. And the reason is, if you remember, I just mentioned that the functional encoding assumes each function is unary. So when you have a binary function, you have to compose it with two unary functions. So it makes things even deeper. So it cannot double the depth. And we see that this is really terrible. So again, perhaps we need to go deeper with a neural net, or perhaps we need to do something else. So basically, I'm looking at you. This is why I'm here, because I would like to establish collaboration with people that are expert in RL or graph neural networks or both, to basically figure out, to help us, how do we solve these type of issues. Okay, so what's next? I think there's many other things we'll discuss with Adam, deeper layers in the network, perhaps looking at other type of networks, like this graph isomorphism network, APPNP. Don't ask me. Adam told me he wants to look at that. I have no idea what this is. Hopefully it talks to you guys. Perhaps tweaking the reward function, looking at much larger languages. These are toy examples. Of course, we're not going to get anything groundbreaking with just 3 rules and a language with 4 things. Having more rewrites. The numbers I've shown you here, these numbers actually are treated as symbols for now. So as far as the encoding is going, we have a node called 1 and a node called 2. What if we have a node called constant, and then there is a magnitude that tells you the value of the constant? Other things, can we discover new rules automatically? So perhaps this set of rules is not complete. Perhaps we can use machine learning to discover better ones. A little bit like theorem proving, where you could find perhaps rules that allows you to jump in the search space a bit faster than having all the tiny step one at a time. Does it make sense what I'm talking about? Yeah. Okay. So to conclude, what we've seen, hopefully what I've managed to convey in this talk, is that equal saturation is a better way to apply compiler optimization, because it will lead to the optimality, but it is currently not used in compilers because of the exponential saturation time. So if we can solve this problem with machine learning and avoid saturation at all, but apply this idea of applying rewrite on knee graph structure, there is a big room for making, having a big impact here. The challenges, exponential nature, avoid saturation if possible, and I think the opportunities, to use my ML to basically tell the compiler what should you do next given this state. And the last thing is the state is captured basically by this equality graph. So I think I will end here. Last picture, this is a photo of my group from a few years ago. There have been people leaving, coming in, and I have 4 students currently actively working on equality saturation in my group, and one of them is Adam, that is just here. Yeah. So thank you very much for your attention, and I'll be happy to take your questions.
Yeah, just let me know if you guys have any questions. I'll pass over the mic.
I don't need a mic, I think.
No. It's for the people online. They won't be able to hear you.
Okay. So I had a question about saturation. If we express the expression into graph, each individual tree can be parallelized, right? The optimizations can be parallelized. So is there an attempt in that direction to optimize?
Yeah, absolutely. So if I understand your question is when we are processing that graph, because the order of the rewrite does not matter, we could apply them kind of in parallel. So I actually have one of my students, Jonathan, I should have left the picture slide, who was actually implemented a new equality saturation library that parallelizes exactly to exploit this property. And he goes a bit a step further. What he does, he also creates, he makes the graph structure immutable, which allows us to not only parallelize, but also speculate. Because there are people that have done some heuristic, they don't use machine learning, but instead what they do, they say, perhaps sometimes you are expanding the E-graph, but you're not going in the good direction, and then you're gonna keep expanding these nodes that will lead to nowhere. So sometimes what people want to do is they kind of want to create a copy of the E-graph and say, let's try explore a bit in that direction. And then if it leads nowhere, let's go back to the original E-graph. This is called rebasing. And you can rebase yourself to a previous version and try your luck somewhere else. Because things grow exponentially, if you start on the wrong track, you might get lost, right?
Right. So, is it promising to move in that direction, or?
I think the best is machine learning. Because these people do it with tricks. They're like, oh, if the rule is too complex, maybe let's not try to apply it too often because that leads to more nodes in the graph. But I'm thinking, machine learning should be able to learn that. Should be able to learn, oh, there are certain rules that perhaps you don't want to apply too often. Because from the training we've observed, they never lead to something good, only rarely. So therefore, just apply it once in a while. But people, again, do these things very manually. They assign probabilities manually on the rules, saying, oh, okay, as a human, I would say, tell my compiler, don't apply this rule too often.
It should be automated.
Absolutely, yeah, I think it should be completely automated. Yeah.
I have a second question, if
Yeah.
there is time. So, because the hardware architecture is evolving, for example, if we have multi-code, so single instruction, multiple nodes performing it, like CUDA. So, how do, like zooming out on your research, so how do you ensure that the hardware utilization is good enough while you're adding this optimizations?
Yeah, so I can give the perfect example. So you can think of your GPU here. This actually work that other people have been doing with equality saturation. You know that you can now have some tensor cores, and you can obviously right? I don't have to tell you that, but and they can do this matrix multiply very quickly. Right? So people have been using, for instance, in the context of C code, to generate CUDA code for the GPU. We know that they have this intrinsic function you can use to basically make use of the tensor core. And then they use equality saturation, kind of tell the compiler, if you find these combinations of loops that actually matches a matrix multiply, try to turn that into a call to this intrinsic function, because we know for that GPU that's going to be good. So the beauty of this approach with equality saturation or rewrite, if you like, is that you design your compiler once, and the rewrites come on the side. They are like an input, like the program. So if tomorrow you have a new feature in your hardware, and the hardware designer exposes it as an intrinsic function, you don't need to rewrite the compiler. You just define the rewrites, the rules that allows you to exploit it. Of saying, oh, the hardware designer now gave me the ability to do, I don't know, a multiplication of two tensors of dimension 10. So I can write that, oh, this intrinsic is equivalent to this program with this multiplication of tensors of dimension 10. And then you give that to the compiler, and you don't have to rewrite the compiler. The saturation engine is written once, and we'll use that as an input, the input program, and then figure out what to do with that.
Okay.
It's very similar to how people write backend in compilers. If you ever talk to LLVM developers, you know, architects design new type of instruction for the CPU all the time, or there are new type of CPU coming out there. And compiler writer have written basically domain-specific languages that allows you to describe your instruction set. And then you can use another compiler that's specialized to generate the compiler backend. So, but here we're really talking about this equality saturation engine. It's something that you write once, and then the rewrites, you can add them however you want.
Okay. So it can be incrementally developed.
Absolutely,
Okay.
yeah.
Okay. Thank you.
Yeah, you're welcome. Thanks for the question. Any questions online, perhaps? So I see something on the chat.
Fabrice, you can actually unmute yourself and then ask it.
Yeah, hi, thanks for the talk. It was really interesting. I'm wondering, is there like a way to use the equality saturation, but with an unsaturated graph based on kind of heuristics instead of just machine learning? And is that a good baseline in the context of these larger graphs where there's normally an exponential cost with regular equality saturation? Or is that a good baseline, or does it not really work in practice, even with like heuristics and such?
So there has been several work in the literature where people have, actually you can find hundreds of papers on equality saturation in the compiler community. People come up with lots of different heuristics, but I would say your heuristic might work very well for one problem, and then you have a different problem and it would just break. So one of my students, the one that works on this idiom recognition, for instance, is actually preparing another paper where he's comparing the different heuristic that exists out there for specific that problem of recognizing idiom, and they just fail. They just don't work. So I think the problem of the heuristic is that they might work for a very limited set of benchmarks, and perhaps if all you care about is multiplying matrices, maybe that's going to be good enough. But they're not going to be general purpose. But people do that, right? That's the kind of the state of the art. They go and write some heuristic because obviously you don't want to wait until saturation. But again, there's no production compiler out there that uses equality saturation at the moment because it remains an unsolved problem. How do you get around that problem of this exponential growth or designing really good heuristic? People don't know how to do that. People are proposing some heuristics, but again, they will never work across all the possible programs you can imagine.
Okay, thank you.
Thank you. Yeah.
Yeah, thanks for the talk. This is really cool. I'm curious for the results you showed at the end with the average rewards for your learning methods. Is this based on the reward function that you wrote a few slides before, like with the penalty?
Yes.
So, like, is there any way you could tell how well this reward function aligns with like performance, like in a real setting, or is this like a reward function that exists outside of your work? Or
no, so we picked that to start. I think Adam is the one that came up with the reward function. Our ultimate goal is actually to reduce the time it takes to apply the optimization. So, and there's totally another aspect here that I've not talked about. So perhaps some rewrites might take longer to apply than others, because, for instance, you first have to pattern match. You have to find this pattern, and then rewriting this into that might take longer than rewriting +1 - 1 0. But for now, we're just ignoring that. We're just counting how many applications we need. Yeah. Do you want to say one more word, Adam, on that?
Yeah. So at the beginning, but maybe in the future, we can progress like average ranking and rewrite it instead of any problems.
have you considered like trying to learn this somehow? Because it's like a kind of like very disappointing, but like extremely difficult problem, at least in my experience. Is like it's so easy to get the reward function wrong, basically. And so like, yeah, like maybe it was the plot before this where like the random agent was like way better than EQSAT, which I guess it makes sense. Like if your penalty is a little too large, then pretty much anything is better than EQSAT, right? Like you just don't change the code at all, and like it's already better than EQSAT. So like maybe if you had examples of like good compiler optimizations, you could extract a reward function somehow. But that's probably also tough. I'm just curious if you guys thought of that.
Yeah, absolutely. You're right. I think I think we could perhaps learn that reward function, right? Or learn the cost of applying an optimization. Right? So this is I had that as just a tiny bullet point under tweaks to the reward function. Right? So this is an avenue to explore. Yeah. Again, for us, we already start to can we learn something? Because even to get these curves, this result there, it took a few months. Because at first we start with a tiny neural net that cannot learn anything because we only have one layer or something like that, right? But again, we would definitely welcome any inputs that you guys may have.
Cool. Yeah, thanks a lot.
Thanks.
When you do the rewrites, if you have a provider in place, then that can give you the time to.
So that's like.
So that would be very accurate.
Yeah, that's like my next step. Yeah, but like all of these because they're so simple, all the rewrites are like 9 and they're all like very direct. But in the future, like we move to bigger cases, I think I have to incorporate that.
How long did you train it for? Because it's just, it's not pre-trained the model, it's really just RL from scratch.
So for these small models, I found 5,000 episodes usually good enough, like good 10,000, but that goes much earlier. For this like new test now, I'm trying to stuff. It's like a bit old now. The results is like it has to be cut out of usually depends on how big the input expression is. Too. So usually 10,000 episodes enough for like these small pieces, and like that's usually
It converges. It stops learning.
yeah, it stops
Oh.
usually. We do these a bit longer, but move from an hour to 4 hours, depends on the computer.
And how big do the graphs get? How many nodes?
Yeah, so that was one of the problems recently, but they can go like, I think right now we can go up to 800 nodes. Or
That takes
maybe
4
1,000.
hours to train. That takes 4 hours to train with the G7.
Not exactly, I usually create like 5 models at the same time, just to see. So it's probably can go faster, but I'm trying to get as much results as fast as possible. Just like,
Okay, thank you.
Yeah. Let's thank the speaker again.
Yep. Thank you. And as I mentioned earlier, we're looking for collaborators. So, you know, Adam is the main brain behind all that. I'm just the one stealing all the work and presenting it. So please reach out to Adam if you're interested to collaborate with us. Okay, thank you.